So last video we learned a little bit about heating and cooling curves, and now we're going to go in and apply all that information about heat capacity and heating and cooling curves to some problems. So we're going to try and do some calculations that one might need to do in certain kinds of occasions. So this example is not so applicable, but it's an interesting application. So how much heat total in kilojoules is needed to convert ice at minus 18 degrees Celsius to steam at 150 degrees Celsius. And for this problem, our mass of ice is going to be 270 grams. So we have 270 grams of ice that we're starting out. And that ice is really cold at minus 18 degrees Celsius, and we're going to figure out how much heat we would need to put in to convert it to steam. Now, although this is a kind of contrived example, you might imagine that there's an example that some sort of chemical engineer or some sort of process designer might need to calculate how much heat energy they have to put in to get a particular process to happen. And this is how they might do it. So, if you were trying to melt your iron and then melt some aluminum and then combine all those and, get it to certain temperatures, the particular reaction would happen and so forth. This might be a calculation that you would have to do. So you would have to know the energy input so that you could plan accordingly for your power needs at your company. So that's a practical example of why somebody might want to do these calculations. So let's think about this at first. So we're going to collect and analyze to do this problem. And a good idea is to draw a heating curve. So we're starting with ice and we're going to steam. So this is going to be heating. So let's draw what's going on. So here's my axes, my x and y axes, a little bit funky shape there. But the x-axis is then going to be the heat that I am putting in, and so that'll be measured in joules or kilojoules. And over here, this is going to be the temperature. We're going to let the temperature be in degrees Celsius. So I start off at minus 18 degrees Celsius, and then we're going to heat this water up from minus 18 degrees Celsius. And we know that something special happens with water at 0 degrees Celsius. That's the melting point, normal melting point. And again at 100 degrees Celsius. I'm going to put that mark in here, 100 degrees Celsius. And finally, our final temperature is going to be up here at 150 degrees Celsius. Okay, so we start here at a temperature of minus 18, and then we're going to add some heat, and what's going to happen is the temperature will go up. But right when we hit 0, we've learned that what happens is that you hit this halt, it's called a halt, and then the temperature remains constant as the ice starts to melt, and then once all of it is melted, it starts to increase again. And so now we're heating the liquid water up from 0 degrees to 100 degrees, and then we hit a halt again. And at that halt point, the temperature remains constant until we have vaporized all of our liquid water into steam. And once all the water has been converted into water vapor, steam, we can begin heating up the steam like that. So here's a sketch then of our cooling curve. So we can kind of divide it into regions. So here's our first region here, 1, and our second region, this flat halt, 2, third region, 3, fourth region, 4, and fifth region, 5. So different processes are going on in each one of these 5 regions, right? We're heating up ice, we are melting the ice, we're heating liquid water, we're vaporizing the water, and then we're heating up the steam, the water vapor. So we're trying to calculate the total heat needed to convert the ice all the way from this point to this top point up here. That's our final state. So we can think of breaking down the heat total, so my little subscript tot for total. The total heat, we can then break it down to the amount of heat we have to add for each one of these little line segments. So we just add up all the heats, Q1 plus Q2, so that'll cover this amount. Then we've got to heat up the water, that's Q3. Then we've got to vaporize the water, that's Q4. And finally, we're going to heat up the water vapor, heat up the steam, that's Q5. So if we can add up all those heats, then we can calculate the total amount of heat that's involved. So we're going to do this problem in steps. And so our first step is phase 1 here. So we're going to go over here in phase 1. What's going on? We're going to heat the ice from negative 18 degrees Celsius to 0 degrees Celsius. So in order to do that, we need a couple of formulas. So we need to calculate the amount of heat. So we need a formula for heat, and we need to relate that to a temperature change. So we've got 2 choices. We've got the MCAT formula, M times CS for solid water times the delta T. So there's our MCAT formula. Or we can use the molar version. So Q is equal to the number of moles times the CP for solid water times the delta T. So both of these relate heat to a temperature change. So one of these formulas will be the one that I want to use. Now what I know from table 5.1 in the book is that the CSP, or the CP, sorry, the molar heat capacity for solid water for ice is 37.1 joules per mole degree Celsius. And so since I know that value, I'm going to use this formula over here to do my calculation. So in order to do that, though, I need to know the number of moles of water. And I wasn't given the number of moles of water. Up here I was told the mass of the ice that I have is 270 grams. So I'm going to have to do a conversion factor. But no worries, we know how to do that. So let's calculate moles of water. N is moles of ice. So we have 270 grams of ice. And the way to convert grams to moles is with molar mass. So we want to get grams to go away. That goes downstairs. We want moles to be our one standing unit. So that goes upstairs. And so there's 1 mole in every, and so we add it up off the periodic table. 18.02 grams is the molar mass of water. And so when we do this calculation, we'll get 15.0 moles of water. So that's how much ice we have. We have 15 moles of water molecules in all that 270 grams of ice. So now we're ready to use our formula for calculating Q. I'm going to go ahead and put a subscript label on this, Q1, because this is for region 1, right? So Q1 is equal to N. What's N? That's our number of moles, 15 moles, times the CP for ice, and so that's 37.1 joules per mole degrees Celsius. Then we're going to multiply that by the temperature change. So what's my temperature change? Delta T is final minus initial, so my final temperature is 0 degrees C. My initial temperature is negative 18, so I've got to take a minus negative 18 degrees Celsius. Minus a minus there is going on. So there's my final temperature, TF, minus my initial temperature, T sub I. There we go. So we punch all this into our calculator very carefully, and we get a number 1.0 times 10 to the 4th joules. Now that's a lot of joules, so we're going to go ahead and convert that into kilojoules. So there are 1,000 joules in a kilojoule, so we just divide that by 1,000, and we get 10 kilojoules as our answer. So that's how much energy we have to put in to heat up the ice. So now we're ready to move on to step 2. So there are going to be a lot of steps, 5 steps. So now we're in region 2, and region 2 is when we're melting the ice. Alright, so we're going to need a formula that tells us about the melting of ice. So what we know is this property called delta H of fusion. So that's the enthalpy change, which at constant pressure is the amount of heat that you have to put in to do this process that we call fusion. And fusion is a scientific word for melting. So it turns out that this is a value that you can look up in tables, and in your book it's listed as 6.01 kilograms per mole. And now this is for water. So this is the delta H of fusion for water, right? The delta H for fusion for copper, metal, or for wax or something will be a different number. So this is the delta H of fusion for water. This number is just telling us that if you have 1 mole of water, you're going to have to put in 6.01 kilojoules of heat energy to melt that one mole of water. Now we don't have 1 mole of water. We have 270 grams. We've already calculated that that is 15 moles. So we're just going to have to multiply those two together. So this is the amount of heat energy for 1 mole. We've got 15. So a formula that we might use is Q is equal to the number of moles that we have times the molar heat of fusion. That's what this is called, delta H sub fusion. There we go. So let's go ahead and substitute our numbers in. We know we've got 15 moles of water. We're going to multiply that by 6.01 kilojoules. That's how much heat we put in per mole. So the moles will cancel out, and that'll give us our answer in kilojoules, and that number is 90, about. So 90 kilojoules. Okay, so that's for region 2. Now moving on to region 3. So region 3, what's going on in region 3? Region 3, we're going to heat 270 grams of liquid water from 0 degrees Celsius to 100 degrees Celsius, because we have to get it from the freezing point of water to the boiling point of water. So again, we need to relate heat, Q, to a temperature change. So we know what formula we're going to use to do that. Let's stick with the formula form that we were using before, N times the molar heat capacity. But this time we need the molar heat capacity for liquid water. And then we multiply that by delta T. So we need to look up our molar heat capacity for liquid water. And again, that's in table 5.1 in your textbook. And it turns out that that number is 75.3 joules per mole degrees Celsius. So now we're ready to plug in all our values. So N is 15 moles again. Molar heat capacity, 75.3 joules per mole degree Celsius. And we multiply by our delta T. So that's final. What's our final temperature? 100 degrees Celsius. Minus our initial temperature, 0 degrees Celsius. Punch all that carefully into our calculator. And the number that we get is 1.13 times 10 to the 5th joules. Again, that's a lot of joules, so we're going to convert that to kilojoules by dividing by 1,000, and so we get 113 kilojoules. By the way, we're going to add all these numbers for each of the steps, 1, 2, 3, 4, and 5 at the end, so they need to be all in the same units when we add them. So you want to make sure that that happens. That's a common mistake on exams, is to leave your numbers like, say, this one would be easy to leave in joules because that's what you're in, whereas our calculation in step 2, the delta H of fusion was given to us in kilojoules. So if you're not careful with your units, you'll make a mistake, and we don't want to do that. So now we're ready to move on to step 4. So what's going on in step 4? Step 4, we're vaporizing 270 grams of liquid water. So we need a formula for that, and just like before, that's going to be Q equals the number of moles times the molar enthalpy, and this time our process is vaporization, so we need delta H vap here. So we need to look up a value for delta H vap, and that's in your textbook. Again, it'll be this number for water, but it's a different number for different substances because it'll take more or less heat to vaporize different substances. So for water, it turns out to be 40.67 kilojoules per mole. So if you have 1 mole of liquid water, you have to put in 40.67 kilojoules to vaporize that 1 mole. Now we've got more than that. We've got 15 moles, so it's going to take a lot more heat. We can use this formula to do the calculation. So Q for this formula is 15 moles times delta H of vaporization, 40.67 kilojoules per mole. And we multiply that out. We get 610 kilojoules. All right, so this is Q for step 4. So I'm going to put a little subscript 4 there. Oh, I think I forgot to do that on my previous answers. Let's go back and notate those just so we're clear. So for step 3, we're going to call that Q3. And for step 2 up here, we're just going to go back and call that Q2. That just helps me keep track since this is a long problem with lots of steps. So finally, we're ready to do our last step. So step 5 then, what are we going to be doing? We're going to be heating 270 grams of water vapor from 100 degrees Celsius to 150 degrees Celsius. All right, again, so this is calculating heat related to a temperature change. So we know a formula to do that. Q is equal to N times Cp, and this time we need the Cp for water vapor. So that will be a different number than the heat capacity for water liquid and ice. So all those substances, they have different heat capacities. They absorb heat in different ways. All right, so we're just going to plug in. We know what these numbers are. We've got 15 moles. We have to look up our Cp for water vapor in our textbook, and it turns out that that number is 33.6 joules per mole degree Celsius. And then we need to multiply by our delta T. So our delta T is going to be, so we're going to multiply by T final, that's 150 degrees C, minus T initial, which is 100 degrees C. And so when we finish this calculation, we'll get Q5 equaling 2.52 times 10 to the 4th joules. We're going to go ahead and convert that into kilojoules, so all our heats are in the same unit, so we divide by 1,000, and that's 25.2 kilojoules. Very good. So now we have all 5 of our heats. We're ready to calculate the total heat. So let's move to where we have some more space to write, way back up here. So here's our original formula for the total amount of heat. So now we're going to just substitute into this formula. So Q total would be equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. We just calculated all those. So if you'll go back and look at your notes, Q1 was 10 kilojoules, Q2 was 90 kilojoules, Q3 was 113 kilojoules, Q4 was 610 kilojoules. Notice how that number is much bigger than all the others, so it takes a lot of heat energy to convert a liquid into a gas. That's because you have to pull apart all of those cohesive forces that are holding the water molecules together. And finally, to heat up the steam, 25.2 kilojoules. So we add up all those numbers, and we get a grand total of 848 kilojoules. Whew, so there's our answer. So this is how much heat energy you would need to convert that amount of water from ice to steam at those temperatures. So even though this problem seems long, if you break it down, each step just involves kind of the same thing. And notice that when we were calculating Q1, Q3, and Q5, we essentially used the same formula. We just had different molar heat capacities. Similarly, when we were calculating Q2 and Q4, we essentially used the same formula. Q is equal to number of moles times the delta H for whatever phase change you're talking about, fusion or vaporization, right? Oh, and by the way, if we ever were doing a problem where we needed the delta H of condensation, how would you find that? Well, you might not find that in a table, but we can use this fact, that the delta H, the molar enthalpy of condensation, well, condensation is just the reverse of vaporization. So that means it's just going to be equal to the negative of the delta H of vaporization. Similarly, if we needed the delta H of solidification, that's just going to be the negative of the delta H of fusion. Right? So it has to be this way because of the first law of thermodynamics. We have to conserve energy. So the energy that we put in to vaporize, that has to be exactly equal to the energy that we would get out if we condense this stuff. If it weren't, we'd be able to create energy. But the first law of thermodynamics says you can't do that. Very good. So we've got one more example that uses some of these techniques. Let's give us a little bit of practice. So I'm just going to clear off some space here and we'll come back and give that problem a try. So in this video we're going to practice another problem that involves heating and cooling. So this problem involves a very practical problem. So how many bags of ice should you buy if you want to ice down some beverages? So we're going to solve this problem the geeked out way rather than just going to the store and getting, like 4 or 5 bags of ice. So let's say that you're going to have a party. Right? So you've gotten 3 cases of tasty beverage. And let's say that the place that we buy the beverages, they're stored at room temperature, right? So we're going to need to cool them down. So we would need to know how much ice to buy. And let's say that ice is sold at my particular store in 10-pound bags. And so we've got to cool our beverages down from room temperature at 25 degrees Celsius so that they're nice and ice cold, because nothing's better than a tasty beverage that's ice cold. So we've got to go from 25 degrees Celsius down to ice cold at 0 degrees Celsius. Okay, so 3 cases is going to be about 72 cans. This is a big party that we're having. And each can contains about 355 milliliters of tasty beverage. And we're going to assume that the ice is initially at minus 8 degrees Celsius in our convenience store freezer. Okay, so we're going to calculate this the geeked out way. We want to know exactly how much ice you would need so that by the time these beverages get exactly to 0 degrees Celsius, you will have melted the last bit of ice that you had, and now you've got ice cold beverages and no ice. So this is the exact amount of ice that you would need to buy. Can we calculate it? Yes, we can. So here we go. Let's do that. So first we're going to use a bit of the first law of thermodynamics. So we're going to be cooling our beverages. So from the beverages perspective, it's an exothermic process. So the beverages are going to be losing heat. Heat's going out of the beverages, right? So the heat, Q, lost by the beverages, the tasty beverages, yum, is going to be equal to, but opposite in sign, to the heat that is gained by the ice, right? So whatever is losing the heat, the system is losing the heat, then the surroundings have to be gaining exactly that amount of heat because we can't create or destroy energy. That's the first law of thermodynamics. So heat lost by the beverages has to be equal but opposite in sign, so Q equals negative the heat Q gained by the ice. So we're going to need to kind of calculate both of these. So knowing how much heat was lost by the beverages, we'll be able to figure out how much ice we need to absorb all of that heat. So that's kind of where we're going. So first off, let's try to calculate this heat lost by the beverage. So we're trying to calculate this amount, the heat lost by the beverage. So first off, we need to know how much beverage do we have. And the reason we're going to need to know how much beverage we have is because we know a way to calculate something about the heat lost, but it all depends on either knowing moles or grams. So we need to know how much tasty beverage. Well, we know that we have 72 cans, right? And each can has 355 milliliters, so 355 milliliters per can. And so just multiplying that out, we get 25,600 milliliters. I told you this was going to be a good party, so we got lots of tasty beverage here. So the cans cancel out, and that tells us how many total milliliters we had. Well, we still need to get that in some way into grams. So we're going to assume that the tasty beverages that we're serving contain mostly water, and that the other flavorings and components in these tasty beverages don't change the composition that much. So it's still mostly water. So we're going to assume mostly water. In that case, we can use this volume and calculate the actual number of moles. So that's what we're going to do. So we've got 25,600 milliliters of a solution, a beverage that is mostly water. So we need to first convert that into grams. So we're going to use the density of water to do that. And the density of water is 1 gram of water in every milliliter. So we have 1 gram of water per every 1 milliliter of water. And so that term right there, this bit right here, we're just multiplying by the density. Now we need to convert this into moles, because some of our formulas are going to involve moles, right? So we did all our calculations in the last example in moles. So we know that there's 1 mole of water off the periodic table in every 18.02 grams of water. Alright, so looking at these calculations, milliliters of water cancel, grams of water cancel, and we get our final answer in moles of water. So we have 1,420 moles of water, and we're going to assume that's how many moles of tasty beverage we have. Alright, so that's good. Now we know how much beverage we have. So now we're ready to think about this heat lost by the beverage. So the beverage is mostly made up of the water, but there's another piece to it as well. So we're going to write here, lost by the beverage. So we want to know the Q total lost by beverage. So that's all a subscript, just a label so I can keep track. So it's actually made of 2 parts. So we first have to cool the liquid part of the beverage down, right? But we also have to cool down the metal cans as well, right? So they're also at 25 degrees Celsius. So the Q for the liquid and the Q for the aluminum cans. So we need to figure out both of those. So let's do the liquid part first. So Q for the liquid. So we can use this formula, number of moles times the molar heat capacity for liquid water, that's our tasty beverage, we're going to assume it's mostly water, times the temperature change. This is just the formula that we were using before, and this will tell us how much heat that we have to remove from this tasty beverage. So we know how many moles we have, that's 1,420 moles. The molar heat capacity of the liquid, we can look that up in table 5.1, and that's 75.3 joules per mole degree Celsius. And our temperature change, final temperature, so we want these beverages to be ice cold, right? So that's 0 degrees Celsius. And our initial temperature, though they were initially at room temperature in the store where we bought them, so that's 25 degrees Celsius. So final minus initial gives us this. And so when we multiply this out, so 0 minus 25 is negative 25, so we're going to get a negative number here, negative 2.67 times 10 to the 6th joules. You might wonder, hey, negative, what does that mean, negative heat? Well, remember, the sign is just telling us the direction of heat flow, and the heat is flowing out of the tasty beverage liquid and into the ice. So this is just giving us direction of heat flow. So this many joules are going to flow out. So now let's think about the aluminum, right? So we need to do the same kind of calculation for the aluminum cans. We need to know some information, though, about the cans. So first off, we need to know what is the mass of a can. So it turns out we can empty a can and go and weigh it real quickly, and we can figure out that a can contains about 12.5 grams of aluminum per can. So that's how much an empty can would weigh. So we can figure out our moles of aluminum through a little calculation. So we're going to do yet another calculation. Yay, we love these things, right? So we've got 72 cans. I told you this is the geeked out way. So 72 cans. And then we know that there's 12.5 grams per can. So we can figure out how much total grams of aluminum we have. So the cans will cancel. So this little conversion right here has told us grams of aluminum. And now we need to convert into moles of aluminum. So there's 1 mole of aluminum in every 26.6 0.98 grams of aluminum. And we can just look that up off the periodic table. So we just divide that, multiply all through, and we get 33.36 moles of aluminum. Alright, so now we're ready to calculate the Q for the aluminum cans, right, for the cans. So we have N, 33.36 moles. So we're using the same formula, N times molar heat capacity times delta T. So now we need to look up the molar heat capacity of aluminum. So that's different than the molar heat capacity of water because it's a different substance. So we look that up in some table somewhere, and we find that that's 24.4 joules per mole degrees Celsius, right? So metals have pretty low heat capacities. Put a little bit of heat in, they get pretty hot. You know that if you've ever put your hand on something metal out in the summer sun, right? Metal gets pretty hot pretty fast. So then we're going to multiply it by our temperature change, which again is 0 for our final temperature, an ice-cold beverage, minus the room temperature that we start out with, it's degrees Celsius. Okay, so we calculate the heat from the aluminum cans, and we figure out that we need to remove 2.3, so removed is the negative sign, 2.03 times 10 to the 4th joules. And we do all this math. Okay, so now let's add up the total amount of heat that we have to remove from the beverages. So Q, let's see, what was my label up here before? Q total lost by beverage. Very good. So Q total lost by beverage. Abbreviate beverage, BEV. And so that's Q for the liquid plus Q for the aluminum. We know both those numbers. So Q for the liquid was negative 2.67 times 10 to the 6th joules. And then we're going to add to that plus the negative 2.03 times 10 to the 4th joules for the aluminum cans. And so that gives us a grand total of negative 2.69 times 10 to the 6th joules. Or, since that's a big number, let's go ahead and convert that into kilojoules. Negative 2.69 times 10 to the 3rd kilojoules. Now we're also converting it into kilojoules because in a minute we need to account for a phase change later, and we want everything to be in the same units, and oftentimes those delta H's of phase changes, those enthalpies for phase changes, are in kilojoules. Okay, so now we know how much heat we have to pull out of all our tasty beverages to cool them down so that they're nice and ice cold. That many kilojoules. So how much ice is it going to take to do that? Well, we need to figure that out next. So now we're going to calculate the heat gained by the ice. So if we think about what's going on with the ice, right? So we're going to be melting the ice. So we're going to start that ice at negative 8 degrees C, right? And here's the heat. And so we're going to be putting in heat from the cans. We're going to be heating it up to 0 degrees Celsius up here. So this is our temperature axis. And then it's going to level out, right? Temperature is going to remain constant. And then we're going to melt all that ice. And right when we get here to this last point where I've drawn this dot, that's where the last of our ice will have melted, and hopefully we will have pulled out exactly this amount of heat, and now our beverages will be ice cold, and we will have used exactly the right amount of ice because we do things right here in chemistry. Okay, so this, again, we can break up into 2 parts. So first, we're going to figure out the total for the ice, and it's broken up into 2 parts. First, there's the heat associated with heating the ice to 0 degrees Celsius, and then we're going to add the heat for melting the ice. So I just keep those 2 labels on, and now I can break that up into 2 parts. So we already know what these equations are because we've done this in our last problem. Alright, so Q is going to be the number of moles of ice that we have times the heat capacity for solid ice, water, right, times our temperature change. So that's this formula, Q for heating the ice. So I'm going to write one big formula here, plus Q for melting the ice. So to melt the ice, we need to know how many moles of ice we have. And we need to multiply this by the delta H of fusion for ice. So we're going to have to look that up. So we're going to look up both these numbers, the heat capacity for ice and the delta H of fusion for water. Now what about number of moles of ice? We don't know that. That's actually what we're looking for, right? We need to know something about how much ice to buy. So if we know how many moles of ice, we can just walk into our convenience store and tell them, hey, I need that many moles of ice. and they'll stare at you. So we'll probably have to tell them in pounds, so we'll have to do some extra conversions. La-di-da, sure, we can do that. All right, so that's what we're going to calculate. So how are we going to calculate this number of moles if we don't know some of these other variables? But the heat that's going to be gained by the ice, we actually do know what that is, because it's got to be equal to the heat that we're trying to take away from our tasty beverages. So we know every variable in this equation. We know the Q, we know the heat capacity, we can look that up, we know the temperature change, so we know every variable but moles. So that's what we're trying to do now. Use some algebra to solve for moles. So let's plug in some numbers here. So we've got N for the ice, and that's the number that we don't yet know. So we look up the heat capacity for water, and we find that for solid water, for ice, we find that that's 37.1 joules per mole degree Celsius. But because ultimately I'm going to want all of my numbers in kilojoules, I'm going to go ahead and convert that into kilojoules. So I'm going to convert 37.1 joules per mole degree Celsius into kilojoules. And so that's going to be 0.0371 kilojoules per mole per degree Celsius. So that is the molar heat capacity in kilojoules for ice. And then we're going to multiply that by our temperature change. So that's going to be final minus initial. So our final temperature is going to be, so the ice has got to warm up, right, to 0 degrees. So our initial temperature minus a minus 8 degrees Celsius, right? All right, so that's an 8-degree temperature change. And then we're going to add this to plus the number of moles of ice, N again, times the delta H of fusion. And so the delta H of fusion, we looked that up for water, and it's 6.01 kilojoules per mole. So that's how much heat energy you have to put in to melt 1 mole of ice. Very good. So looking at this equation, I've got a whole bunch of numbers in an N, so I'm going to factor that N out. So the N comes outside. And then up here I've got 0.0371 times 0 minus a minus 8, so that's just plus 8. So I can multiply 0.0371 times 8. What number do I get? I get 0.2968. And the degrees Celsius will have canceled out, right? So my units will be kilojoules per mole there, plus the 6.01 kilojoules per mole. And that's what I get when I factor the N out. Now these two numbers both have the same units, kilojoules per mole, so I can add those. So I'm going to add those two numbers together, and I get N times 6.31 kilojoules per mole. Alright, so if I knew the number of moles of ice, this would tell me the heat. So now we're ready to finish up our problem here, and so we're going to go back to that original statement I told you from the first law and say that the heat that goes into the ice is equal to, but opposite in sign, to the heat that's lost by the beverages. Right? So we're going to use that relationship. So the heat from the ice, that's going to be the number of moles. That's the formula that I just wrote down right up here. It's going to be the number of moles of ice times 6.31 kilojoules per mole. And that equals the negative of the Q for the beverages. What is the Q for the beverage? Let's go back up here. Here it is. It's this number that I calculated. That's the total heat, total lost by beverages. So that's negative 2.69 times 10 to the third kilojoules. So I'm going to put that number in here. So we have a negative 2.69 times 10 to the third kilojoules. So it's important that you keep track of your signs, right? So this negative sign right here came from this minus sign right here. And that's because the heat that goes in has a different direction from the perspective of the beverage, so we have to switch the sign. And then this sign up here came from our previous calculation. Okay, so now if we look at this equation, we can solve this for N. So let's do that. So number of moles of ice is going to be equal to negative times a negative is a positive, so 2.69 times 10 to the third kilojoules divided by 6.31 kilojoules per mole. And the kilojoules will cancel out, and that gives us a value of 4.26 times 10 to the second moles of ice. So that's how much ice we're going to need to cool our beverages. So of course you can't go into the store and ask for that number of moles of ice, so we're going to need to convert that into pounds. So what we're going to first do is convert that into grams, and then we can convert the grams into pounds. But we'll have to look up a conversion factor for grams to pounds. But we know how to go from moles to grams. So 4.26 times 10 to the second moles of ice, and so ice is water, right? Solid water. And so we want to convert that into grams. So we need the molar mass for water. So we want grams upstairs. We're trying to get rid of moles. That goes downstairs. So there's 18.02 grams of water per mole. Alright, so very good. There's our first step, moles to grams. Now we need to convert grams to pounds. So we look up a conversion factor, and on the internet will tell you that 1 pound is equivalent to 453.6 grams. So now our grams will cancel out, and our final answer is 16.9 pounds of ice. Alright, so at our store, ice is sold in 10-pound bags. So, after all this geeked out calculation, we know exactly how much ice to buy. To be certain, we want to get 2 bags, right? Because 1 is not enough. Whew, alright. So, I don't know about you, but I'm ready for a tasty beverage.